Morning friends, the last portion of this chapter wave optics, that is depends on the scattering and also the phenomena of reflection. Already we discussed in chapter 9 in wave optics. Right? What is the phenomena of the scattering? Now, when the sunlight is incident on the very small particle of the atmosphere, so its direction is changes, and due to that reason, the sky is shown the bluish, the sun rise and sunset shown the yellowish reddish, while the cloud in the sky is shown the bluish, shown the white. Already we discussed in chapter 9. Here we are going to discuss about the polarization by scattering phenomena, or what is the effect of the scattering on polarization. Okay. Last we also discussed about the unpolarized light and polarized light. Unpolarized light, that means the light vectors, that means the electric field vector oscillate in all direction in a plane perpendicular to the direction of propagation of a wave or the ray. So that is known as the unpolarized light. So in short, in unpolarized light is like this way. Here the electric field vector are oscillate in all direction in a plane. This plane is perpendicular to the direction of propagation. That means suppose the wave is propagated in this direction. So we do the plane that perpendicular to the direction of propagation. So in this plane, the electric field vector are oscillate in all directions. So that is the unpolarized light. While the plane polarized light, that means the oscillation of electric field component is parallel to each other and also parallel to the plane perpendicular to the direction of propagation. That means as we do the plane like this way, there is perpendicular to the direction of propagation of a wave. So here the electric field component are oscillate parallel to the plane. Suppose that is the plane. So electric field vector are oscillate parallel to the plane. So that is known as plane polarized light, or the plane polarization. It is also possible the electric field component of the vector are oscillate perpendicular to this plane, like to this way, inside, outside. In a plane, this plane is perpendicular to the direction of propagation. So that is known as the polarized light. And polarization, that means to obtain the polarized light from unpolarized light, that is known as the polarization. So keep in mind this concept, we are going to discuss about the polarization by scattering. So for that purpose, we show that the sky is shown the bluish, but the light from the clear blue portion of the sky shows the rise and fall of intensity. The sky is shown, that is the bluish by our naked eye, but when this sky is observed by a Polaroid glass, at that time, and as we rotate the Polaroid, at that time what's happened? So the intensity of this blue color is either increase or decrease. So there is a first sentence, the light from the clear blue portion of the sky shows a rise and fall of intensity when viewed through a Polaroid. Which is rotated. That means as we rotate the Polaroid, already we discussed about the Polaroid, thin plastic sheet having the pass axis, or the tourmaline plate having its one pass axis. As we are observing the sky by this type of the Polaroid, and as we rotate the Polaroid, so the intensity of the blue color coming from the sky are increase and decrease. What is the reason? The sunlight changes its direction on colliding with the molecule of the Earth's atmosphere, and that is known as the scattering phenomenon. What is the reason? Because the sunlight changes its direction on colliding with the molecule of Earth's atmosphere, and that is known as the scattering. that is known as the scattered. Okay. Now, here in figure, the light coming from the sun traveling horizontal, incident on the molecule of the atmosphere. So before the colliding with the molecule of the atmosphere, so here there is the unpolarized light. There is the incident sunlight, there is the unpolarized light. Due to the colliding with the molecule of the Earth's atmosphere, suppose the sunlight is traveling in this direction, or the change its direction by 90 degrees with the original direction, and there is entered the eye of an observer. That means the observer is looking towards the sun at 90 degree direction. At that time what's happened? The observer can't see this oscillation of electric field vector or the light vector, because there is parallel to our direction of observation. So that is not shown. Now, the charge accelerating in the direction parallel to the plane do not radiate any energy, because it has no transverse component in the direction, in this downward direction. Therefore, the observer can't feel this type of the oscillation of light vector. So for that purpose, the incident sunlight is unpolarized. In unpolarized light, the dot shows the polarization perpendicular to the figure, perpendicular to the plane of the figure. While the double arrow, this double arrow shows the polarization in the plane, polarization in the plane. So here we show that separate figure only for information. Here double arrow shows the oscillation of electric field vector parallel to the plane. This plane is perpendicular to the direction of propagation. Okay. Now the dot represents this. The oscillation of electric field vector perpendicular to the plane, this plane. And this plane is represented by dot. So dot shows the polarization plane perpendicular to the plane of the figure. And double arrow shows the polarization in the plane. Now what's happened in atmosphere? The charge is like the electron. Actually, the atmosphere of the Earth is made up of the charges positive and negative. Okay. Now, the electron in the molecule of the incident ray, under the effect of the electric field, perform the motion in both of these directions. So, what are the electrons of the molecule of incident ray? Due to the effect of the electric field, these electrons are oscillating in both directions. Vertically up, down, and also in, out direction to the field. So when the observer looking at 90 degree direction to the sun, the charge is oscillating parallel to the double arrow. What are the charges oscillating in up and down direction? Do not radiate the energy towards the observer. Observer is observing the sun in the direction perpendicular to the direction of the sun. Now, the charges oscillating parallel to the double arrow do not radiate any energy towards the observer. Because what is the reason? The acceleration has no transverse component. Only the acceleration takes place in vertically up and downward direction, no transverse component. Therefore, the energy radiated is zero in perpendicular direction. Therefore, the radiation scattered by the molecule is therefore represented by only dots. Therefore, the radiation scattered by the molecule is only represented by the dots. So it is the polarized perpendicular to the plane of the figure. So here we obtain the dot only. Not this vertical oscillation of the charges, because that is the coincide with the direction of observation. Therefore, the effect is not observed by the observer, only this perpendicular effect is observed. So, this process is known as the polarization by scattering. That means this explains the polarization of scattered light from the sky. So, this question is asked in 4 marks for this year, 2020. Only you have to attend these 2 paragraphs and figure. So very short question and answer for 4 marks. Very easy. Our concept must be clear about the polarized and unpolarized light and what's happened. Due to when the sunlight is observed by the polaroid, and as we rotate the polaroid, so what's happened? The intensity of this sunlight is increased and decreased. What is the reason? Because the direction of the sunlight is continuously changes due to the colliding with the molecule of the Earth's atmosphere. Now, after the discussion of the polarization by scattering, now how we obtain the plane polarized light by the phenomena of reflection. So that is known as the polarization by reflection. So that is the important question for this year. Now listen, for each and every board exam, one question always asked from this portion of polarization, either the polarization by the scattering or the polarization by reflection. For this year, that is the most important. Explain the polarization of light by the reflection and explain the Brewster's law, or discuss the Brewster's law and obtain the equation. Effective index of the given material is equal to tangent of angle of polarization IB or theta P. That means we have to obtain this equation eta or the mu is equal to 10 IB. For that purpose, already we discussed about the Malus law. Malus discovered that when light is incident on a surface of the transparent medium, the reflected ray is partially plane polarized. And the reflected ray is partially polarized. Now listen here. The two contradictory sentences here. The reflected ray is partially plane polarized, while the reflected ray is partially polarized only. Plane polarized, that means here the electric field vector or the light vector oscillating perpendicular to the plane. This plane is perpendicular to the direction of propagation, that is denoted by the dot. That means the reflected ray is represented by the dot. Why? The reflected ray is not totally plane polarized. That is only polarized. That means the light vector are oscillating both directions, parallel to the plane of polarization and also perpendicular to the plane of polarization. So both components are present in reflected ray, while only the light vectors oscillating perpendicular to the plane are present in reflected ray. Again, the Malus discovered that when ray of light incident on a surface of transparent medium, the reflected ray is partially plane polarized and reflected ray is partially polarized. Okay. Now, the state of polarization of reflected ray depends on the angle of incidence. Not for all the angle of incidence, the light is incident on the surface. Always this type of the phenomena, that means the reflected is partially plane polarized and reflected is polarized, is not obtained. For definite angle of incidence, we obtain this state. Okay. Now, As shown in the figure, we consider the light is incident on the surface of transparent medium. So here the both phenomena, reflection and refraction, take place. So reflected ray is totally plane polarized. Reflected ray is totally plane polarized. In this state, in reflected ray, all light vectors are parallel to each other and perpendicular to the plane of incidence. Yeah, what's happened? There is oscillating in out direction, inward outward direction. Light vectors are oscillate like this way. So this type of the light vector obtained in reflected ray, therefore the reflected ray is totally plane polarized. Again, so reflected ray is totally plane polarized, and in this state, in reflected ray, all light vectors are parallel to each other. They are parallel to each other and also oscillating perpendicular to the plane of incidence. Plane of incidence is this, that means the plane of a figure. Now, this type of the light vectors are known as the sigma component. That is known as the sigma component. Now, in reflected ray contains 15% of sigma component of incident ray. Again, what are the reflected ray? There is the totally plane polarized. In this reflected ray, light vectors are oscillate perpendicular to the plane of the figure of the incidence plane. This component are known as the sigma component. In reflected ray, it contains 15% sigma component. 15% sigma component only present in reflected ray, and due to that result, the reflected ray is faint. That means the intensity of the reflected ray is less. Therefore, the reflection phenomena during the reflection is not shown clearly. Because in reflected ray, only 15% component of incident ray. Hence, the reflected ray is faint. Okay. While in reflected ray, what's happened? In reflected ray, remaining 85% sigma component and all pi components. Pi components, that means the light vectors oscillate parallel to the plane of incidence. Here the plane of incidence is the plane of the board. What are the light vectors are oscillate parallel to the plane of a board or the plane of a figure? Are 100%. That means the pi component, all the pi component and remaining 85 sigma component are present in reflected ray. Therefore, the intensity of the reflected ray is more than the reflected ray, but slightly less than the incident ray. Slightly less than the incident ray. Again, in reflected ray, what's happened? Remaining 85 sigma component and all pi component. Pi component, that means the light vector oscillating parallel to the plane of oscillation or the plane of incidence plane. All pi components are present, and thus the reflected ray or the intensity of the reflected ray is more than the reflected ray but less than the incident ray, and hence it is slightly faint compared to the incident ray. Thus, when a ray of light is incident on a surface of transparent medium at some definite angle of incidence, the reflected ray is totally plane polarized, and such an angle is known as the angle of polarization, this angle. Again, when the incident ray is incident on the surface of a transparent medium, the reflected ray is totally plane polarized. In this condition, the angle of incidence is known as the angle of polarization, and that is also known as the BREWSTER'S angle. That is known as the BREWSTER'S angle. And it is denoted by IB or theta B. Theta B, the angle of polarization, and IB for BREWSTER'S angle. That is the notation according to our text. Again, hence very easy. Now, how we explain the polarization by reflection? For that purpose, we first keep the concept of the malus. Malus discovered that when the light is incident on the surface of a transparent medium, here the reflection and refraction take place. The reflected ray is partially plane polarized and reflected ray is partially polarized. State of polarization, how much polarization take place of reflected ray is depends on the angle of incidence. As the angle of incidence changes, so the state of polarization and also the reflected ray changes. For that purpose, as shown in the figure, when a ray of light incident on a surface of a transparent medium, the reflected ray is totally plane polarized. Now, in this state, the reflected ray, all light vectors are parallel to each other and perpendicular to the plane of incidence. This is known as the sigma component. Thus, in reflected ray contain only 15% sigma component of incident ray. Hence, the reflected ray is fat. That means the intensity of the reflected ray is less than the intensity of the incident ray. So very poor in intensity of reflected ray. Now, in reflected ray, there are remaining 85% sigma component and all pi components. Hence, it's slightly fat than the incident ray. But there is the very intensive, for the intensity of reflected ray is more than the reflected ray, but less than the incident ray. Thus, when a ray of light is incident on the surface of transparent medium at some definite angle, the reflected ray is totally plane polarized. The angle of incidence is known as the angle of polarization. That is also known as the BREWSTER'S angle, and it is denoted by IB or theta p. Now we obtain the BREWSTER'S law. That means the mu or the n is equal to tan theta p or the tan I. Okay, now we are obtaining the BREWSTER'S law. For that purpose, we are applying the Snell's law at a given point. Now the Snell's law, again we further diagram like to this way. That is the angle of incidence, incident ray. Angle of incidence is IB or theta p. That is the reflected ray. That is reflected ray, and that is our reflected ray. Angle of reflection is R, small r. R is equal to here pi by 2 minus IB for the theta p. That is the incident ray. That is the medium 1. That is the A medium. Refractive index theta 1 is equal to 1, for the n1 is equal to 1. That is the medium 2, that is the transparent medium. And the refractive index n2 is equal to, suppose, the mu. We are applying the Snell's law at this point. Now, what is the equation of the Snell's law? n1 sin I is equal to n2 sin R. Right? So here I have written n1 sin R is equal to n2 sin R. Here n1 for A medium, the refractive index is 1. n2 for the transparent medium, refractive index is n or mu. Angle of incidence I is equal to IB or theta p, and R is equal to angle of reflection. R is equal to pi by 2 minus IB. Pi by 2 minus IB. Or we can also add the pi by 2 minus theta p. Now we substitute this value in Snell's law equation. So 1 into sine IB is equal to mu sine R is equal to pi by 2 minus IB. Therefore, sine pi by 2 minus theta, cos theta. Therefore, sine IB is equal to mu cos IB. Mu cos IB. Therefore, mu is equal to sine IB upon cos IB. Sine upon cos, that is the tan. And the mu is equal to tan IB or the tan theta B. This equation is known as the BREWSTER'S law. That is known as the BREWSTER'S law. We derive this equation from the Snell's law. N1 sin R is equal to N2 sin R. Here we substitute the particular value of N1, N2, I, and R. We obtain mu is equal to tan IB or the tan theta B. Now, what is the statement of this equation or the BREWSTER'S law? For that purpose, when a ray reflected from the surface of a transparent object or the transparent medium is totally plane polarized, the tangent of angle of incidence is equal to the refractive index of the transparent medium or the transparent object. Again, when the ray is reflected from the surface of a transparent medium, there is our transparent medium. This reflected ray is plane polarized. So in this state or this condition, the tangent of angle of incidence is equal to the refractive index of our transparent medium. Again, the statement is that when a ray is reflected from a surface of transparent medium or the object is totally plane polarized, the tangent of angle of incidence is equal to the refractive index of the transparent object or the transparent medium. So this statement is known as the BREWSTER'S law. So here chapter 10 is completed. There is the polarization by the reflection, and we also discussed about the BREWSTER'S law. This figure is not important, but for our knowledge how we obtain or how we apply the Snell's law for given figure. Due to that reason, I do again here this figure. That is only for information.